anomaly preserving compactifications and confinement in Yang-Mills theory.
Thank you very much for the invitation to the organizers, especially, and I'm very pleased to be here. Today I will talk about the idea of adiabatic continuity and its implication for confinement in Yang-Mills theory and QCD. So let me first define what I mean by adiabatic continuity. So this is a relatively new idea, like 15 years or so, and the idea is that in non-supersymmetric gauge theories, or even some generic quantum field theories, one can connect strong coupling, non-perturbative strong coupling phenomena to weak coupling without having any phase transition, without any intervening phase transitions. So one can question whether this is possible or not. I will show you examples that it is indeed possible. But almost, since mid-70s, it's a repeated culture that all of these phenomena, for example, things like confinement, chiral symmetry breaking, etc., are necessarily taking place at strong coupling. But these beliefs also exist in the current literature, but they are not true. In the last 15 years or so, we understood quite a bit about the adiabatic continuity on R3 cross S1. This S1 is necessarily not a thermal circle. And with judicious compactification, appropriate compactification, boundary conditions, and other content, you can continuously connect the theory on R4 to arbitrarily small S1. But this is not the topic that I will talk about today. It's not R3 cross S1. Rather, I will talk about another example of adiabatic continuity which provides some new insights. So let me start with two challenging questions. One of them is that can we continuously connect four-dimensional physics of some generic non-supersymmetric theories to two-dimensional physics without having any intervening phase transition? If we could achieve this, this would be great because we understand much better about two-dimensional theories, and it can also provide new insights. Another question, which seems unrelated at this stage, but they are ultimately related. So it's a technical question. How do we formulate semi-classics in two-hoofed flux background in a thermodynamic limit? This is, believe it or not properly addressed for generic gauge theories. There is an example I will mention where it is addressed. So let me start with the adiabatic continuity on R2 times T2. You can also replace R2 with some arbitrary two manifold. Okay. So I will consider SUN gauge theories generically, and at large R2 times T2, locally speaking, there is no distinction between an SUN gauge theory, SUN with the insertion of a fixed two-hoofed flux, as well as PSUN theory, which is SUN mod ZN, where we gauge one form part of the one form symmetry. And locally, these theories are same. You can actually move from this theory to that theory by coupling this quantum field theory to a topological quantum field theory. So locally, they are same. That means that, for example, if you are looking to the mass gap, they are identical. But at small T2 times R2, studying SUN theory with the insertion of some units of two-hoofed flux is far more superior than other choices. And there is a good reason for that, because the flux stabilizes the zero form part of the center symmetry which is otherwise swollen, which is otherwise broken at small t2. And I will show this very concretely. This thing may sound a little bit strange, but it is well known in a small subcommunity of the lattice gauge theory in the context of twisted Teguchi-Kawai matrix model, which is a matrix model equivalent to infinite volume lattice gauge theory at infinite n. And one can also see imprints of this kind of stability, how it works and what role it plays in the classic calculation of supersymmetric index in SUN super Yang-Mills theory. Now, you may probably have seen talks about this 't Hooft flux background used to put kinematical constraints on the dynamics of the theories. Actually, in several years, Seiberg and his collaborators used to, use one-form symmetries as well as mixed anomalies to constrain possible IR phases. But my goal today is not that. My goal is to study semi-classical dynamics in these flux backgrounds. And one can more or less discuss any theory. I will restrict myself to Yang-Mills theory and QCD with fundamental fermions, but you can also study other theories. So let me start with Yang-Mills theory on R2 times T2. So let's take a symmetric T2, and let's say it's sufficiently small, smaller than the strong scale, called compactified direction x3 and x4. So classical minima is given in terms of flat connections. So if 3, 4 is equal to 0, let's name the Polyakov loops P3 and P4. And each holonomy takes value in the maximal torus. And the classical moduli is two product of these maximal torus modeled with the permutation group Sn. The question is, what happens to this classical moduli space quantum mechanically, and what happens to it in the presence of the 't Hooft flux? And we will obtain two opposite answers to this question. So, in the absence of 't Hooft flux, first let me state that the Yang-Mills theory is a one-form symmetry. And when you compactify the theory on R2 times T2, this reduces to a two-dimensional one-form symmetry and two-dimensional zero-form symmetries. And let's say this is the compactification radius, and if it's sufficiently small circle, you can do a one-loop potential for one-loop calculation for the holonomy potential, and you learn that these Polyakov loops are unstable. In this phase, this Zn cross Zn part of the center symmetry is spontaneously broken, while at large T2, they are not broken. So there is a phase transition as you go from this large T2 to small T2. I will in a moment show that when you insert 't Hooft flux, there is no phase transition. And let me tell you why. So activating 't Hooft flux is same thing as turning a two-form field for the one-form symmetry. So the standard way that 't Hooft did this is following, and you can do this in any theory with adjoint matter. So if you have some adjoint matter, you can on T2, you can put these transition functions, and the consistency at the corner here tells you that these transition functions must obey this cocycle condition. And this n here is a gauge invariant quantity called 't Hooft flux. So, in the presence of these background 't Hooft flux, the Polyakov loops are defined not only by just holonomies, but by transition functions times holonomies. And you can show that so one can show that the Polyakov loop in this background acquire two values, clock and shift. They are mutually non-commuting. You can think of this thing as two non-commuting Higgs fields, and it tells you that you can reduce SUN gauge structure at sufficiently long distances down to Zn. This is interesting, actually. So I want to also make another remark. If you look to perturbative spectrum theory, a perturbative spectrum of the theory on R2 times T2, usually when we do Kazakh-line decomposition, the modes are quantized in units of 2 pi over L. But with this insertion of 2 Hooft flux and twisted boundary condition, they are quantized in units of 2 pi over NL. In fact, notice that even if L is fixed, you take n to infinity, the modes form a continuum. This is related to the idea of large and volume independence or Eguchi-Kawai reduction. But the thing it tells you that there are no zero modes here for the gauge field anymore. And all the gauge fields are gapped. So if you look to the Wilson loops, to all orders in perturbation theory, you can show that they obey perimeter law. So the infrared theory, to all orders in perturbation theory, is a Zn TQFT. The question is, what happens non-perturbatively? Is this TQFT destabilized? So non-perturbatively, it's a different story, because in this 2 Hooft flux background, let's say you activate N12 and N34. These are 2 Hooft fluxes on 1, 2, and 3, 4. You can actually show that topological charge is quantized in fractional units, in units of 1 over n. If there are topological configuration which satisfy this BPS bound, then the action is quantized in these fractional units, 8 pi squared divided by g squared n. These analytic solutions, at least on R2 times T2, are not analytically, the solutions are not analytically known. But from lattice, there is a compelling evidence that they exist. There are localized lumps that can be seen explicitly on the lattice. Furthermore, you can show that if you take one of these localized lumps and put it inside a Wilson loop acquires classically this phase. It's the vortex inside the loop. So there is a non-trivial mutual statistics between the Wilson loop and this vortex. Now, since these configurations are finite action, that means they have finite fugacity. That means if you take a snapshot of the Euclidean vacuum, they will proliferate in this Euclidean vacuum. And you can do a dilute gas analysis, reliable dilute semiclassical analysis based on this. And let us momentarily ignore the Wilson loop. You can actually consider just partition functions semi-classically, and you sum over all these fractional configurations, but the constraint is, since you are in the SUN theory, topological charge must be integer quantized. That's the origin of the constraint. And that gives you the multi-branch structure of the vacuum, and notice that the object, the topological object that enters to this story has an action which is 1 over n of the instanton action, and they do not die off at n infinity. These fractional instantons survive in the 2 Hooft large n limit. So when you insert the Wilson loop, the only difference in this story is that, as I told you, if you have these vortices inside the Wilson loop, there are some pure phases that you have to attach to this calculation. Only in the calculation, only these phase factor changes. So from this thing, you can extract the string tension, and you can obtain string tension in this limit. And it has along with its theta dependence, and it is a multi-branch structure. So this is very promising because it also obeys the usual analytic rule. The string tensions, the spectrum of the string tensions is dictated by Zn one-form symmetry. Now, you can ask why this compactification is special. The reason for this is that on arbitrarily large form manifold, let's say on T4 or R4, there is a mixed anomaly between one-form symmetry and CP. So if you do a CP transformation to the partition function in the background of these two-form gauge fields, there is a mild violation here. And it tells you that, this thing tells you that the vacuum at theta equal pi cannot be trivially gapped phase. Now, when you do this compactification, I told you, I just decompose it appropriately, and there is also this insertion of two flux. You can show that the same anomaly survives compactification, in particular the anomaly between theta periodicity and one-form symmetry survives compactification so long as two-hoofed flux is non-zero. This is the reason this thing is special. And this is also the reason that this is also consistent with semi-classical analysis. You can ask the question whether we can do similar analysis in QCD with fundamental quarks. Two Hooft asked himself the same question, and his answer is no. The reason is that whenever you have fundamental quark, you lose the one-form symmetry. Zn one-form symmetry is gone. So he says you cannot impose twisted boundary condition consistently. It leads to unacceptable jumps at the boundary. But this argument is a little bit too fast. The reason it is too fast, because in gauge theory, the genuine global symmetry, if you consider the relation between baryon number symmetry and quark number symmetry, there is this quotient. So this is the common quotient of the U1 baryon and SUN gauge structure. This Zn is part of the gauge redundancy. Now you can impose two Hooft's twisted boundary condition by invoking this U1 background. And there are two things entering here. You can undo the jumps due to this G3 and G4, which would appear for the fundamental fermions by invoking these U1 baryon backgrounds. Now, what happens when you do that? Something very interesting happens, and this part took me by surprise, and it is, realization of my collaborator Yuya Tanizaki. It's, I think it was, yeah. And the interesting thing is we can study Dirac operator in the background of this twisted boundary condition. And we can solve for the Dirac operator, and we can show that there are NF two-dimensional Dirac fermions. And you can solve them explicitly. They are very beautiful solutions. They are given in terms of Jacobi theta functions, which are quasi-periodic, just reflecting the fact that we are on a non-trivial bundle. But at hand, we have 2D NF flavors of Mestel's Dirac fermions, and we know that we can use non-abelian bosonization, and we can map this system to level 1 UNF WZW theory. And you can appreciate that this started to look a lot like chiral Lagrangian. At least the first term looks like it. The second term looks something different, but it will go there. It is almost chiral Lagrangian, but you can also ask the effect of these fractional instantons, center vortices, and you can show that they generate this term. And this term actually lifts one of the degrees of freedom, and you end up with NF minus 1 degrees of freedom. And the infrared theory is SUNF level 1 Vesumino-Witten theory with central charge NF minus 1. Now, this sounds very promising. Furthermore, if you take the large n limit, the center vortex term gives you this thing which provides a mass for the eta prime mass, but this is nothing but semi-classical derivation of the Witten-Veneziano formula. So if one assumes adiabatic continuity, this construction is very intimately related to the derivation of the chiral Lagrangian, and let me show this, what I mean more precisely. Okay. So let's go back to R4. We believe that in QCD with fundamental representation quarks, with few number of quarks, the chiral symmetry is broken. The infrared physics is described in terms of chiral Lagrangian. Let's compactify this theory to a very large T2 times R2. Now, if we consider the physics at length scales larger than the T2 size, Then the model reduces to two-dimensional principal chiral model. Principal chiral model is a beautiful two-dimensional matrix model. It's asymptotically free and it has a mass cap. So the thing we obtain doesn't resemble to anything like the small T2 limits. But since we are considering the theory in the U1 baryon background, we are turning on a magnetic flux for the U1 baryon field. We must couple it to baryon current. We must couple the U1 baryon field to baryon current. And this changes the story quite a bit. So the baryon current or skyrmion current is given in this form. The baryon number gauge fields and baryon current coupling can be written in a 5-dimensional space in this form. Now let us consider the compactification of this 5-dimensional space M5 to M3 times T2. You can integrate over T2. There is a non-trivial baryon number flux passing through T2, and this is the term that you obtain. This is exactly the Vesumi-Noviton term in 2 dimensions. So this theory, if you put appropriate F pi's and L's in appropriate places, it actually flows to level 1 Vesumi-Noviton term. So it provides a perfect matching between a microscopic QCD analysis and macroscopic chiral Lagrangian analysis. So it looks like arbitrarily small T2 theory is adiabatically connected to arbitrarily large T2 theory. Now, let me wrap up with this outlook. So as far as we understand now, all the known non-trivial strong coupling phenomena, such as confinement, chiral symmetry breaking, mass gap, multi-branch structure, etc., can be continuously connected to weak coupling. I provided a few examples of this idea right now. In all the cases, both on R3 cross S1 as well as R2 times T2, the non-perturbative expansion, semi-classical expansion, is always reliable in this domain, and it is always controlled by 1 over n of the instant on action. And as such, this thing survives in the 2 Hooftian large n limit. Now, I didn't tell you the story on R3 cross S1 because, I did that very long time ago in 2007 or 8, and it's also an equally interesting story. On R3 cross S1, there are 2 very interesting mechanisms. One of them is monopole instanton mechanism. The other is magnetic baryon mechanism. Whenever there is something attached to monopole instanton, either due to zero mode or something else, they never lead to confinement. You always have to consider some critical points at infinity, some correlated events of the monopole instantons, and magnetic baryons is such examples. They have magnetic charge and no zero modes, so they can generate confinement. But the interesting thing is, this is the mechanism on R3 cross S1. These objects have charges in the core-root lattice. They have trivial mutual statistics with the Wilson loop. On the other hand, the objects that we came across in this talk and this work are center vortices on R2 times T2. They have non-trivial mutual statistics with the Wilson loops. Both of them are fractional topological charge, 1 over n, and fractional action, 1 over n, but they are different. So it's a puzzle how to connect these 2 reliable semi-classical regimes. And finally, I didn't tell you the story for other cases, supersymmetric or QCD with many, 2-index representation fermions or even chiral theories can be addressed in this context. All of the strong coupling expectations, matches with the weak coupling results. And it is impossible not to speculate that these fractional instanton saddles, as well as the critical points at infinities, may actually provide a complete basis in the sense of resurgence. Maybe these saddles, it's a suspicion, NO hop, maybe these saddles will form a complete basis. Then this is a very interesting possibility. Then it tells us that we may do something more even on R4 in infinite volume concerning Young-Mills and QCD. Thank you very much.
Did I understand it correctly that it was important for you that n is finite as opposed to infinite for this to work?
The region of validity of the semi-classical analysis is actually interesting. It is L times n times lambda less than 1. So for semi-classical analysis, so you shrink to this small L regime, which scales as 1 over n. There is a similar thing in cyber-Witten theory discovered by, Douglas and Schenker. So, and if you also look to the size of these center vortices, they scale with n. When n gets large, they start to overlap. So, in this sense, this analysis, weak coupling analysis, is actually valid at arbitrary n, but you have to keep n fixed, but take L to arbitrarily small values for the semi-classics to be completely reliable.
Then I do not understand why you're saying that confinement is continuously connected. Because in 4 dimensions, confinement is, I would say, the most sharp at infinite n, because flux tube is the most sharply defined object. And then for you, it seems like confinement behaves differently and it's n-dependent.
No, it's very easy to address that question. In the sense of all gauge invariant order parameters, there is no transition as you go from this small circle regime to small torus regime to large torus regime. They are adiabatically connected. The order parameters you have at your disposal are Polyakov loops. They are 0 at small t2, 0 at large t2. You are done.
There was one more.
Yes.
So I vaguely remember that in the case of S3 compactification, at weak coupling we can see confinement, but we couldn't see chiral symmetry breaking. So I wonder if detail of the...
So S3 curvature behaves like temperature in some sense. So at small S3 you cannot see chiral symmetry breaking, but on R3 times S1 or R2 times T2, there is no other scale entering to the game. So here you can see both chiral symmetry breaking or,
so
as
here
well as
is
confinement.
adiabatic continuity that you are using flat compact
Flat,
space
of course,
is crucial.
Yeah.
Thanks for the nice talk. This JJ bar deformation, did you worry about it? Because it's known to destabilize these principal chiral models.
Say that again.
So if you take the SU2 level 1, there's a marginal coupling JJ bar.
Oh no, and I didn't study it.
If it has the wrong sign, then you flow to a gapped phase. So it's not a super stable phase.
Okay, yeah, we need to look at it. So I didn't look at it.
Let's end. And just a moment, there's an announcement from the organizers.
Okay. So now comes